Hai semua, jumpa lagi untuk sesi yang kedua untuk hari ini. Kita akan bincangkan subtopik 2.10 Understanding Work, Energy, Power and Efficiency. Ini adalah bab yang kedua, tingkatan 4 dalam topik besarnya Motion and Forces. So we just go straight to the business. Choose the correct word in the bracket. So what is work? Work is the product of applied force and displacement. So dalam formula we can write it as W for work equal to force multiplied by displacement. Remember that the force and displacement, they must be parallel, in the same direction, parallel. When the work is done, we can also say that energy is transferred. That's why work, is very related to energy. So work in joule, energy also in joule. When it comes to the unit. So the work done is equal to the amount of energy transferred, and the SI unit for work is joule. But then what is watt here? So watt here is actually the unit for power. That is power, whereby power equal to energy divided by time. If you are to define power, so we can say that power is the rate of change of energy, or the rate of energy dissipation. So that is power. So B, fill the blank with the correct answer. So number 1, kinetic energy is the energy of an object due to its motion. So whenever something is in motion, so that object must possess the kinetic energy. 2, gravitational potential energy, energy of an object due to its position. Kerana kedudukan dia. Number 3, the principle of conservation of energy states that energy can be transferred from one form to another, but it cannot be created or destroyed. So this thing here, make sure you know, alright, what is stated in the principle of conservation of energy. Number 4, the principle of conservation of energy explains that the total amount of energy always remains unchanged. So that's why we use the term here conservation. In bahasa Melayu, conservation is keabadian. So the total amount of energy always remain the same. C, state true or false. Power is the rate of doing work. So remember that P just now equal to E over T. So we have mentioned that when E is interrelated with W. So I can write also W over T. So what is power? Power is the rate of doing work. So this is true. Efficiency of a device, is the percentage of the energy input that is transformed into useful energy. So you need to understand the statement here. It simply says that I can write this as P output, over P input multiplied by 100%. okay, but P equal to E over T, okay. So I can write here E output over T divided by E input over T, okay, multiply by 100%. So what you will end up with would be E output over E input multiply by 100%. So this is what is stated in this statement. Okay, so they are the same thing. So this statement is true. Alright, now D. State the transformations of energy. A durian falls to the ground. Okay, falls to the ground. So it must be falling from a height. So here I have gravitational potential energy. Okay, I will just put this as EP. Yeah? Okay, so EP is the potential energy due to gravity, gravitational potential gravity. Okay, fall to the ground. So it fall, so meaning to say it will be in motion, correct? So here I have kinetic energy. And when it hit the ground, definitely you will hear sound. So some of the energy will be transformed into sound energy. Okay, now a bulb connected to a dry cell, okay, to a dry cell lights up. So what energy changes do we have? So it must start with the electrical energy. Okay, what does this thing do? It lights up a bulb. So lights up the bulb, meaning to say that the electrical energy will be converted or be transformed into light energy, correct? Okay, light energy. But at the same time, it also being transformed into heat energy. That's why when we hold a bulb, we can feel the heat. Okay, a bell rings when the switch is pressed. So a bell ring due to the electricity. So again, here I have electrical energy. Okay, so what happened? The bell rings. So bell rings. So rings sound. Okay, so transform into sound energy. But before it becomes sound energy, definitely there must be kinetic energy. Okay, because the hammer will be hitting the gong. Okay, the motion of an arrow when an archer releases the string. So when we pull the string, so we are having elastic potential energy. Correct? So what happens if we release the string? Okay, the arrow will be flying off, correct? So it's in motion, so I have kinetic energy. Okay, let's move on. Work done. Okay, you see the first one here, I have an object, okay, being pulled, okay, to a distance of s. So here is our displacement. Okay, so remember just now we said that work equal to force multiplied by displacement. Okay, and I can see that the force and also the displacement, they are in the same direction. Okay, they are parallel to each other. Okay, so here they are already parallel. Now let's go to this one here. Okay, I have a force. Okay, here is the pulling force at an angle of theta. Okay, I am pulling this box to this new position. Okay, so this is my displacement. Okay, so my displacement is horizontal. Therefore, I need to find the horizontal components of this force. Okay, so we have to resolve this force into the horizontal component and the vertical component, but we don't look at the vertical component because it's not doing anything. Okay, what is moving the box is the horizontal components of the force. So again, here we are going to use our trigonometry. So here is the force. Okay, so I can draw my right triangle. So over here is my f sub x. Here is my f. Okay, and here the angle is theta. So we are interested in this f sub x. Okay, so angle and f sub x, they are adjacent. So if they are adjacent, so we are going to use our cos theta. So cos theta equals f sub x over f. Therefore, f sub x equals f cos theta. So what is the work done? Okay, work done, again, it equal fs. Okay, and remember I said just now that f and s, they must be parallel. So that's why we are looking at f sub x, because f sub x is parallel to my s here. Okay, so this f is actually my f sub x multiplied by s, but f sub x is equal to f cos theta. Okay, and then multiply by s. So I can rewrite this as fs multiplied by cos theta. All right. So we go to the next question. Okay, diagram A and B shows a boy pushing a load and a weightlifter lifting a load of 60 kilograms. You are to calculate the work done by the boy. Okay, by the boy first. So work. So the boy is pushing the box, okay, horizontally, and the displacement is 2 meter. So my pushing force is already parallel to my displacement. All right. So W equal Fs. My force is 20 Newton. My displacement is 2 meter. So that will be 40. Okay, 40 Newton meter. Or Newton meter can also be written as Joule. Now, what about the weight lifter here? Okay, so the weight here, it has a force of going down. That's the weight, right? And then the displacement is this way, it's going up. So are they two parallel? Yes, they are parallel. So we are going to use our formula W equals Fs. So what is my F? My F would be the weight of this load, right? And here it is given that the mass is 60 kilogram. So my W in this whole system, that will be 60 multiplied by 10, correct? That will be 600 Newton. Okay, so force is 600 Newton, and then the displacement, okay, in the picture, the displacement from ground here to this position, the displacement is 2 meter. So just write here 2 meter. So the work done is 1200 Newton meter. Okay, or we can also write Newton meter as Joule. Okay, simple, right? Okay, number 4. Asman is pulling a box with a force of 50 Newton at an angle of 60 degrees from the horizontal. Calculate the work done to move the box to a distance of 3 meter. Okay, so the displacement is 3 meter. So I have a force going up. That is 50 Newton. Okay, the force is going up, it is slanted, but the box here is moving horizontal. So what do I need to do? I need to find the horizontal components of this 50 Newton. So I can draw my right triangle. Alright, so the force is going up like this, so it simply tell us it is going to the right and it goes up. Alright, so here is my F sub x, which is parallel to my displacement. Okay, so the angle and F sub x, they are adjacent. So if they are adjacent, so we are going to use cos. Okay, so cos of 60 degree equals to F sub x. We divide that by the hypotenuse, that will be F. Okay, therefore F sub x equals F multiplied by cos 60. Okay, and our F is 50 multiplied by cos 60 degree. So we will end up with 25 Newton. Therefore, the work done is F sub x multiplied by the displacement. Okay, F sub x is 25 Newton, and then our displacement is 3 meter. So the work done is 75 Newton meter. Okay, or we can write this as 75 Joule. Simple, right? Okay. Let's go to question 5. Sammy releases 2 kilogram metal ball from a building of 40-meter height. Okay, you are to take the acceleration due to gravity as 10 meter per second. Okay, so I have a ball here. The ball here is 2 kilogram. Okay, so the weight of the ball, W equals mg. Okay, so m is 2, g is 10, so the weight is 20 Newton. That's the weight of the ball. Okay, at the height of 40 meter. Okay, at the height. Okay, height of 40 meter, the ball, it has gravitational potential energy. It's due to the position of the ball. Okay, B. Just before the ball hit the ground, the maximum energy that it has would be the kinetic energy. Maximum is the kinetic energy. The minimum would be the gravitational potential energy. This one here would become 0. Okay, it hit the ground. So the ball is here. If the ball is here, so my displacement or my h is 0. Alright, so if we look at our formula, EP, the gravitational potential energy, EP equal to mgh. H is 0, okay, this thing is 0, therefore everything must be 0. Okay, C. Calculate, okay, the energy of the metal ball at the height of 40 meter. It asks for energy, okay. So energy is very simple. At the height of 40 meter, what energy does it possess? That will be the gravitational potential energy. That will be mgh. Okay, and then m, okay, given in the question, the ball is 2 kilogram, g is 10, okay, and the height is 40 meter. So just do your calculation. You should be able to get 800 joule. Okay, C2. Calculate the kinetic energy of the metal ball. Okay, I missed out ball here before it hit the ground. Remember the principle of conservation of energy. Okay, the total energy up here. Okay, I put here as initial. Okay, the total energy up here compared to the total energy down here, I put this as the final energy. Okay, these two, they must be the same. Alright, it is stated in the principle of conservation of energy. So what initial energy do I have here? Okay, I have EP plus EK in this case, but my EK is 0 because the ball is yet to move. So I only have mgh, EP only. Okay, down here I also have EP, okay, plus EK. But down here my EP is 0. Why 0? Because the height would be 0. So the final here, alright, the energy that we have only EK, so EK is 1 over 2 mv squared. Alright, and then by using our principle of energy conservation, okay, so E initial must equal to the E final. So E initial I have mgh must equal to 1 over 2 mv squared. Okay, so that we get from the principle of conservation of energy. Okay, so here the question asks, what is the kinetic energy of the metal ball before it hit the ground? So automatically this kinetic energy must equals 800 joule. We have shown that thing just now in the picture. So what is the principle used in C2? Okay, the principle used is the principle of conservation of energy. Alright, so let's move on. A motor lifting a weight 1 kilogram to a height of 4 meters in 4 seconds. So I have a weight, alright, a weight here being lifted up to a new position. Okay, the distance here would be 4 meters, and then the mass of this is 1 kilogram. Okay, time taken is 4 seconds. So calculate the power of the motor. So to calculate power, so power equals to E over T, or we can also write this as W over T. So in order to answer this question, I need to find what is my work done. Alright, so work done equals Fs. Okay, so S would be the displacement from this point to this point. That will be 4 meters. What about our F? Okay, the mass of the weight is 1 kilogram. Therefore, the weight would be 1 multiplied by 10. That will be 10 Newton. So this is the force. Okay, so work equal to force, that will be 10 Newton, multiplied by displacement is 4 meters. So the work done would be 40 Newton meter. Now remember, we can also write this as 40 joule. Okay, but we haven't answered the question. The question asks for power. Okay, so power equals to W over T. So by definition, power is the rate of doing work. Okay, so work done is 40 joule. Okay, here is 40 joule divided by the time. Time is 4 seconds. So that will give us 10 joule per second. Okay, or we can also write 10 joule per second as watt. Okay, that is the unit for power. Okay, now next one, calculate the efficiency of the motor. So if I look here, the input energy supply to the motor in 1 second is 20 joule. Okay, so 1 second in 20 joule. That is our input. Okay, so input, it says 20 joule in 1 second. So what is this? This is actually the power. The input power is 20 joule per second, or equivalent to 20 watt. Okay, so how do we find efficiency? Okay, so efficiency equals P output, okay, P output divided by P input and multiply by 100%. Okay, so what is my P output? Okay, P output will be up here, and that is the power of the motor when we do the calculation by means of the displacement just now. Alright, so the P output is only 10 watt, but the input is 20 watt. So multiply by 100%, so the efficiency is merely 50%. Okay, sometimes when we talk about efficiency, okay, sometimes we will see this word ideal. Okay, so whenever we see the word ideal, it simply means that the efficiency is 100%. Okay, so no energy is being wasted. But in the real world, there is no ideal thingy. Yeah? It always being lost to the surrounding. Alright, so we go to 2.11, appreciating the importance of maximizing the efficiency of devices. Okay, so this is sort of a repetition of the one that we have done before. So above, the conversions of energy would be from electrical to heat energy, okay, and also light energy. And energy is lost as heat. Okay, why? Due to the resistance. Okay, the resistance in the filament. Okay, petrol engine. You use petrol, so that will be chemical energy. Okay, if you use diesel, it's also chemical energy. So what happened to this chemical energy? It will be converted, transformed into kinetic energy, because you are going to move the engine or the part in the engine. So that will give us the kinetic energy. So in what ways are energy lost? So energy lost as heat and also sound. Alright. So this loss of energy is due to the friction, especially in the engine. Okay, electric fan. Before we can see it is moving, there will be the kinetic energy. What comes before that? So here it must be electrical. Okay, so electrical energy converted into kinetic energy. So in what way energy can be lost? Energy can be lost as heat. Okay, it's due to the resistance in the coil and also the bearing. Alright, battery is to produce electrical, right? But what comes before electrical? What do we have in the battery? We have electrolyte. Alright, so electrolyte is a chemical. So we start with chemical energy, okay, being transformed into electrical energy. Okay, and we do have loss of energy, that will be in terms of heat. Why? Because of the resistance. Okay, resistance in the electrolyte. So this gives rise to the internal resistance. Okay, we have learned this in Form 5. We used small r for this. Okay, we move on. Underline the correct statement. So most of the energy in mechanical devices lost as heat and sound. Okay, this is very true. Okay, as heat. This is due to the friction. Okay, 2. A major cause of inefficiency in machine is due to friction. Okay, I have mentioned it just now up here. So this is also true. Okay, 3. The output energy of devices always more than input energy. You are saying here that the the output energy is greater than the input. This will never happen. Okay, so this one here must be false. The output must always be less than or equal to our input energy. Okay, 4. Maximizing the efficiency of devices makes the best use of the input energy and reduces energy wastage. So this is a true statement. Okay, 5. Maximizing the efficiency of devices help to conserve energy resources. Okay, this one here is also a very true statement. And lastly, when energy transformation takes place, not all of the energy is used to do useful work. So if this is true, yes, this is true. Okay, that's why our efficiency in the real world will be very difficult to reach 100%. Okay, so not all of the energy is used to do useful work. Some will be lost to the surrounding. Alright, so we go to 2.12, understanding elasticity. Alright, so you are given a list of words up here. Okay, so fill in the blank. The property of materials that can return to its original shape or size when the external force no longer acts on it. This is known as elasticity. So if you are asked to define what is elasticity, that would be the ability of an object to return to its original shape or size, okay, when the external force is no longer acting on it. That is elasticity. Okay, 2. Of a spring is the maximum force that can be applied to a spring. Okay, the maximum force that can be applied to a spring such that the spring will be able to be restored to its original length, okay, when the force is removed. So what is this? This is actually our elastic limit. Okay, so if you pull anything with a force that does not exceed the elastic limit, okay, then the spring, it will return to its original length. But if you exceed the elastic limit, the spring will not be able to return to its original length. Okay, because you go beyond the elastic limit. And then Hooke's law. Okay, what does Hooke's law say? Hooke's law simply says that the extension of a spring is directly, okay, is directly proportional to the applied force, okay, provided that the elastic limit is not exceeded. Okay, so what this means is you can only apply Hooke's law if the elastic limit is not reached. Okay, so from this statement I can write that F equal to Kx. Okay, whereby F is the force constant and then F is the force on the spring, K is the force constant. Okay, force constant of the spring. Okay, which we sometimes call this as the spring constant. And X is the extension of the spring. It can also be compression, but basically the same thing. It's simply positive and also negative. Alright, so when a spring that is stretched or compressed, okay, then we say the spring stores elastic potential energy. Okay, throughout I'll be using E sub S, okay, to represent my elastic potential energy. Okay, 5. When a force acts on a spring, so what is done? That will be work. Okay, so work is done. The work done is stored as elastic potential energy. So applications of elasticity. So here a cushion. Okay, a cushion is used to support our body when we sit on it. Okay, B here, this one you just cancel. Okay, B enable passengers in a car to feel comfortable even when it travel on a bumpy road. So that is our car absorber, right? Okay, so here is car absorber. Okay, C used to measure mass or weight which is stretched when a load is hung on it. So this one here is our spring balance. Okay, we go to B, factors that affect the elasticity of a spring. So what are the factors? Okay, so there are 4 factors that affect the elasticity of a spring. The length, the diameter of the spring, the coil itself, and the diameter of the spring wire, the wire that make up the spring, and 4th, the type of material. So let's see the length first. Okay, so here the shorter the spring, the larger the force constant. If for diameter of spring, the larger the diameter of the spring, the smaller the force constant. Diameter of spring wire, okay, so here the larger the diameter of the spring wire, or the thicker, semakin tebal the diameter of spring wire, the larger the force constant of the spring. And 4th, the type of material. So here just put here elasticity. Alright. Sometimes you will hear me using the words soft and stiff. Okay. Soft versus stiff. Okay. Lembut and keras. Okay. So looking at this, the greater the length, okay, so what happened? It will become stiffer or softer. Okay, the greater the length, it will become softer. Okay, so meaning to say that the spring will be extended easier compared to a short spring. Alright, diameter of the spring. If I increase the diameter, so what happened? Alright, so if I increase the diameter of the spring, it also become softer. Diameter of the wire, if I increase it, then this one will become stiffer. Okay, so that sum up the effect of the change in the factors that affect the elasticity. Okay, the force extension graph for two springs R and S are shown below. Complete the table that follows. Okay, so you have to complete this table. So the first one, the gradient of the graph for spring R and spring S. Okay, so if I look here, okay, here gradient for R, that will be y divided by our x, correct? So y I have 40 Newton, 40 Newton, yes, divided by my x is 5. So that will be 8. Okay, 8 Newton per centimeter. And then my gradient for S here, okay, y is 40. Okay, and then my x is 10. So that will be 4. 4 Newton per centimeter. Alright, so we fill in our table here. The gradient for this one is 8, and then for S is 4. Alright, so the gradient of the graph is 8, therefore the force constant of the spring is also 8. So here is 4. Okay, why? Because the gradient of the graph will give us the value of our force constant. Okay, so force constant, that will be our K, correct? K equal to gradient of the graph. Okay, so force needed to extend 1 centimeter of the spring. Okay, so if I look at here, for 1 cm I need 8 Newton. Here for 1 cm I need 4 Newton. Okay, so looking at this, which one is stiffer? For this one, I need 8 Newton to extend the spring by 1 cm. For spring S, I only need 4. So meaning to say, spring R is stiffer. Spring S is softer. Okay. Now, the area under the graph when the spring is extended by 5 centimeter. Okay, by 5 centimeter. You have to find the area under the graph. So from this point to this point. So for R, area under the graph, you see here, that will be 5 and then going up is 40, correct? So area under the graph for R equal to 1 over 2 multiplied by the base is 5 multiplied by the height, that will be 40. Okay, So that will give us, okay, 2 here will be 20. So this is 100 watt. Okay, so force X multiplied by the y-axis. Okay, so that will be Newton centimeter. So I can convert that to meter. That will be 1, okay, 1 Newton meter. Okay, so Newton meter, this one here, if I put it in symbol form, for quantity, Newton is the unit for force, meter is the unit for displacement. So what is this F multiplied by S? This is our work. So what is the unit? Newton meter or joule. So I can also write 1 Newton meter as 1 joule. Okay, that is the work done for R when the spring is extended by 5 centimeter. Now, let's calculate the area under the graph for S. Okay, so we are referring to this area here. Extended only 5 cm. So I have 1 over 2 multiplied by 5, and the height of that triangle is only 20. So here I have 50. Okay, 50 Newton centimeter. Okay, this 5 is in centimeter, right? And this 20 will be in Newton. Okay, here is in Newton. So I convert cm to meter. You should be able to get 0.5 Newton meter. Or you can also write this as 0.5 joule. Okay, let's go back to our table. So the area under the graph when the spring is extended by 5 cm, this is 100 Newton centimeter, equivalent to 1 Newton meter. Okay, for spring S, that will be 50 Newton centimeter, okay, equivalent to 0.5 Newton meter. Okay, elastic potential energy when the spring is extended by 5 centimeter. Okay, you see here also 5 centimeter. So what is the elastic potential energy? So if we go up here just now, we have seen that the area under the graph is actually our work, and work is interrelated with energy. Okay, so work is energy, energy is work. All right, so if the area under the graph for spring R is 1 Newton meter, then the elastic potential energy here would be 1. So here 0.5 for spring S, so the elastic potential energy is 0.5 joule. So from the graph, okay, we may conclude that spring R, okay, is stiffer compared to spring S. So when each spring is extended by 5 cm, spring R, okay, store more elastic potential energy than spring S. Okay, we have seen here. So R is store 1 joule, whereas spring S it only stores 0.5 joule. Okay, so what can we conclude from these two statements? You see here, R stiffer, R store more elastic potential energy. So we can also say that the stiffer the spring, the more elastic potential energy is being stored. All right. So let's go to this question. The figure below shows the arrangements of apparatus in an experiment to determine the relationship between the extension E of a spring T with weight W. The relationship of E and W is shown in the graph. Okay, so you're given a graph. Okay, I have a weight here. So I have a weight force going down. There is my W. Here is our weight. Okay. And this is the graph that you get from doing this experiment. Okay, so based on the graph marked with the cross X, the elastic limit of the spring. So where is our elastic limit? So I have a graph here. This one here seems to be a very straight line until to a point, okay, whereby the line start to bend. Okay, it start to bend. So I can put here as my X. Okay, so here is my X. But you have to label it on the graph itself, not here. All right. So the moment the line start to bend, so that is where our elastic limit is. All right. So if I look down here, I have a straight line, correct? Straight line from this point to this point. I have a straight line, and that line start from 0, 0, the origin. So for this line, okay, our force in this case is W. Okay, W is directly proportional to our E, only up to this point here. But beyond this point, W is no longer directly proportional to E. Okay, do you follow me? All right, now name the law that is related to the graph before the elastic limit is exceeded. So what law says that F is directly proportional to the extension? That is the Hooke's law. So state the relationship between W and E before the elastic limit. So it is directly proportional. Okay. Determine the value of E when W is 8 Newton. Show on the graph how you determine the value of E. So this one, I don't think you have problem with this. So when W is 8, okay, maybe I need to make my line a bit thicker. Okay, if my W is 8, and then you read what is E from your graph. Okay, so we go down here. So here we read is as 3.3, correct? Okay, so 3.3 centimeter. But you have to show this on the graph because the question asks you to do so. Okay, how do you get 3.3? So you have to draw this line. Okay, and then down here that will be 3.3 centimeter. 3.3 centimeter. Okay, so we move on. The spring stores energy when it is extended. Name the type of energy stored in the spring. Well, very easy question. That one must be elastic potential energy. Calculate the force constant of the spring in SI unit. Okay, so remember what our force constant equal to? Okay, so force constant, that is our K. the small k equal to the gradient of the graph. Okay, so just plug in the value. Just now we have found the coordinate here. Okay, hold on, I make my line thicker. Okay, the coordinate here, my x is 3.3 and my y is 8. Okay, and here is my origin, so the coordinate will be 0 and 0. All right, so use that two coordinate to calculate the gradient of the graph. All right, so the gradient of the graph, from your math class you learn gradient equal to y2 minus y1 divided by x2 minus x1. Okay, so your k equals to 8 minus 0 divided by 3.3 minus 0. Okay, my y-axis just now is in Newton and my x-axis is in centimeter. Okay, so you do the calculation, you should be able to get 2.42 Newton per centimeter. You can try to do the conversion from centimeter to meter. Okay, so if you do the conversion, you should be able to get the answer 242 Newton per meter. Okay, now 3. Calculate the area under the graph when the spring is extended from 0 to 4. Okay, extended from 0 to 4. So we are talking about from here to here. So again, I have to read my graph. Okay, what is the value of that y? So it is here. Okay, so my y here, if I draw my line solid, because I want to calculate my area under the graph. So here is 10 and then here I have 4. Okay, so the area under the graph, all right, so area, we have a triangle, correct? So it's 1 over 2 times the base. Okay, the base is 4 centimeter times the height is 10 Newton. So what do you have? I have 20 Newton centimeter. Okay, this one we can convert to Newton meter, right? So if you do the conversion correctly, you should be able to get 0.2 Newton meter, or we can write it also as 0.2 joule. Okay, now calculate the energy stored in the spring when it is extended by 4 cm. So extended by 4 cm, meaning to say our E is 4. The extension is 4 centimeter. But then what is energy? How do we get energy from the graph just now? Alright, so the energy being stored, okay, this is our elastic potential energy, correct? This energy equals to the area under the graph. Okay, when the spring is being extended by 4 centimeter, and we have calculated this up here just now. You see here from 0 to 4. All right, so no need to repeat the calculation. So the area under the graph is 0.2 2 joule. Okay, so what is the relationship between area under the graph and the energy stored in the spring? They are the same. All right, so I can write here area under the graph. Right, so area under the graph is equal to the energy stored in the spring. Okay, we go to the next one here, a continuation of that question. Another spring T is added parallel with the spring T as shown in the figure. Okay, so the springs here are identical. Okay, sketch the graph of W against E for this experiment on the graph. So here is the original graph when we use only one spring. What happened to this graph if I have two springs connected parallel? Okay, they are parallel. In other words, we are having parallel lah. Okay, so remember that we have learned this. If I have only one spring being extended by a load, it makes extension of X. If I have two identical spring, okay, and then being extended by the same load, so what is the extension? The extension will be X over 2. 2 because I have two spring. If I have three spring, okay, three spring and being extended by the same load, then the extension will be X over, yes, over 3. Okay, so looking at this, okay, now my arrangement, I have two spring, okay, two spring in parallel. So we are using this picture here. Okay, so can you see that my extension become half? It's X over 2 is half of the original extension. All right, now, so suppose just now we have seen when W is 10, the weight is 10, the extension is 4, right? So if I have this arrangement, the original extension is 4, correct? But if I put another spring, okay, with this arrangement, what happened to this extension? It will become half. Okay, from 4 it will go to this point here, right? So half of the original extension, and then we just draw the line. Okay, so just draw the line. I'm freehand, but you have to use your ruler. So draw the line. Oops, sorry. Draw the line to this point. Okay, so this is the new graph. Okay, the new sketch of the graph if you have this arrangement. All right, I hope you can follow our discussion for this question. Okay, so that's about it for today. So we shall see again next week. Okay, bye bye.